Okay. So quick recap. Yesterday we were talking about the a point called a centroid, which is the intersection points, the point of concurrency of all the medians of a triangle. The median, go back to yesterday, is if you start at a vertex and you go to the midpoint of an opposite side, that's a median. So where the medians cross the point is a centroid. Anybody remember the mathematical relationship within the medians when you have a centroid? That'll be part of the assignment today. So there's a mathematical relationship between the parts of a median if you know where the centroid is. Zach?
Yeah. Something that's 1/3.
Yeah. So the centroid basically splits each median into two parts. And the shorter part is always 1/3 the length of the entire median. The longer part is always 2/3 the length of the entire median, which means that the relationship between the short and the long part is that the longer part is twice the length of the shorter part, or the shorter part is half the length of the longer part. So, and we finished up yesterday with kind of a long problem, using we used distance formula. That didn't work out very well. So then we switched over to slope intercept form from point slope form. We had to figure out slope and all that kind of stuff as well. And kind of, well, a little bit, unfortunately, we're going to have to do that again today for the very last example in example 4. So we'll get to that in a few minutes. So last thing we're talking about here is altitudes of triangles. Now, an altitude starts from a vertex, just like a lot of these things do. The only one that doesn't actually start from a vertex necessarily is the perpendicular bisectors of the triangles, which goes back to a couple of weeks ago. That was the circumcenter. The incenter was on the angle bisector, which starts at a vertex. Yesterday, the medians, those started at a vertex, and altitudes also start at a vertex. However, what's different about an altitude than median is that from the vertex, it doesn't go to the midpoint of the opposite side. It is instead perpendicular to the opposite side. So an altitude of a triangle is a segment from a vertex of the triangle to the line containing the opposite side that is perpendicular to that side. So the line BD, or the segment BD, is perpendicular to AC, therefore BD would be the altitude. Now, an altitude can lie on the interior of a triangle, like this one here, or in the case of this triangle, which happens to be obtuse, the altitude over here is actually outside of the triangle, which is kind of interesting. An altitude does not have to intersect the opposite side in order for it to be perpendicular. Does that make sense? It doesn't actually have to cross through the opposite side in order for it to be perpendicular to the opposite side. This little dotted line is not actually part of this side right here. So the altitude BD does not intersect the opposite side AC, but it's still perpendicular to the opposite side AC, even though it doesn't actually cross it. So an altitude does not have to intersect an opposite side in order for it to be perpendicular to that opposite side. So BD is an altitude from B to the line containing AC, and that is true for both of those triangles. Every triangle has 3 altitudes, just like it has 3 perpendicular bisectors, just like it has 3 angle bisectors, just like it has 3 medians. It also has 3 altitudes. If extended, the altitudes of a triangle are concurrent. What does concurrent mean? Not quite. Concurrent. The altitudes are concurrent.
Oh.
We reviewed this yesterday. Yeah, so if you go back to page 350, when three or more lines intersect at a common point, the lines are called concurrent lines. So basically, the altitudes, all 3 altitudes intersect at the same point, which means that the altitudes are concurrent because all 3 of them intersect at the same point. So point of concurrency, all 3 lines intersect at the same point. That would be point P here. The point of concurrency is called the orthocenter. So P is the orthocenter. Yesterday, the point of intersection was called the what? Point of intersection of the medians was called what? The centroid, yes. The week before spring break, the point of concurrency for the angle bisectors was called the incenter. And then the first lesson, going back to lesson 6.1, the point of concurrency for the perpendicular bisectors was called the circumcenter. So we have 4 points of concurrence. One of them is for the perpendicular bisectors. That was the circumcenter, which is the same distance from each vertex of a triangle. The second one was called the incenter, which is the point of concurrency of the angle bisectors. That point is equidistant from each side of a triangle. Yesterday, the intersection of the medians with the centroid. That was that 2/3, 1/3 relationship. And then the orthocenter is the intersection of the altitudes, and there isn't a mathematical relationship to speak of. It's just a place. Doesn't really have anything special about it. Actually, the coolest thing about, I think, the centroid yesterday is not so much the 2/3, 1/3 thing. It's the fact that it's the balancing point, right? It gives equal weight to the other parts of the triangle. So it actually balances on that point, which I think is kind of cool. But with the orthocenter, the intersection of the altitudes, there is no special relationship mathematically. But aside from the fact that they are concurrent, they all intersect at the same place. So the lines containing altitudes AF, so AF is an altitude because it is perpendicular to the side BC. CD is an altitude because it is perpendicular to the side AB. And then BG is an altitude because it's perpendicular to the side AC. All three of those lines intersect at one point, P, which is the orthocenter of that. So, using vertices once again. Here we go. So we are going to walk through this one step by step. It's basically what we did yesterday. We're going to have to use equations of lines in order to work through this. I'm thinking we're going to go ahead and use this space up here to do the algebra that we need to do. So we'll get to that in a little bit. But there's a lot more room for us to like work things out down here. But it's the same type of problem that we saw yesterday. So if you were gone yesterday, figuring out a point of intersection is very similar regardless of if you're finding the circumcenter, the incenter, the centroid, or the orthocenter. It's all very similar, just is the difference of what type of line you're drawing through the triangle. But locating that point is basically the same math. So the vertices of triangle ABC are at point A, 4, 0. So let's get that point on there. 1, 2, 3, 4 zeros right there. That's point A. We put an A right underneath it. Point B is at -2, 4. That'll be left 2 and up 4. There's point B. And then point C is at 0, 6. That's going to be not going left or right at all, but it will be going up 6 spots. So there's our vertices of triangle ABC. And we will go ahead and connect up all 3 sides here to draw our triangle. And we're trying to figure out where the orthocenter is, which means we need to figure out how to draw the altitudes in on this particular diagram. So we've got our triangle ABC. The orthocenter is the intersection of all 3 altitudes. However, how many altitudes do we actually need to have on here? We need at least 1, but we actually need 2. Because if we're going to figure out where they intersect, we got to have more than 1 of them. So we'll get 2 of them. We don't need all 3 though, basically, because if 2 of them intersect at one place, the third one will intersect at that same place. So that's just kind of like repetitive and we don't need to. So it says to find the orthocenter, find the point where 2 of the 3 altitudes intersect. Right there, it tells us, find 2 of them. So find equations of the altitudes. This is where we were going with yesterday. If you find the equations of the altitude, it says find an equation of the altitude from B to AC. So basically, from point B, we have to draw a line that is perpendicular from B to this line right here. And it actually tells us what to do. It says the slope of AC is blank. So we have to figure out the slope of this line right here. And we don't need to use the slope formula. We can just count the points. So if we go from C down to A, how far down are we going and how far over are we going? To get from C to A, how far down, how far over? down 6 over 4. If we're talking about rise over run with slope, which we are, down 6 means -6 over 4 means 4. So the fraction would be -6 over 4, but that reduces. What does it reduce to? -3 over 2. Good. Which means that every point on this line, if you count down 3, 1, 2, 3, and over 2, 1, 2, hey, look at that. There's another point right there on that line. So the slope of this line is -3 over 2. The reason why we need the slope of that line is because the altitude from point B to this line needs to be perpendicular to this line. And if we're talking about perpendicular slope, we can actually figure out the slope of the line that is perpendicular to it. So because the slope of AC is -3 over 2, the slope of the altitude, which is perpendicular to AC, is, anybody know? What is the relationship between perpendicular slopes? -3 over 2 turns into what if it's perpendicular? Flip it, good, and turns positive. Good. So what's that going to be? There you go, 2/3. There you go. I love it. Yeah, you're right. So perpendicular to -3 over 2 is positive 2/3, opposite reciprocal. Perpendicular slopes are opposite reciprocal. So if it starts negative, it becomes positive, and you flip the fraction over. If it starts positive, you turn it negative, and you flip the fraction over. So the slope from B to this line is a slope of 2/3. So you're going to use the slope and point B on the altitude to find the equation of the line, which we'll get to in a second. But from point B, we need to go up 2 and over 3, because the line is going to originate from point B because it has to be from the vertex perpendicular to C over here, or perpendicular to CA. So if we go up 2 and over 3, because that's the slope of the line we're using, we go 1, 2, and then 1, 2, 3. Those 2 points will contain that line. And we can actually do this again, up 2 and then 1, 2, 3 over that way, just to get ourselves a little bit more detail in that. So that line looks like that. That is an altitude. So we have an altitude from point B through the side of the triangle AC. Now the issue that we've got here, we're just finishing up the notes from yesterday. So what we need to do next is we've got to figure out the equation of that line. So figuring out the equation of that line means we need to start in point slope form, just like we've been doing, and then convert to slope intercept. So I think I can actually fit this in right here. We're gonna have to write kind of small, but we'll be able to get it. Because we have the slope of the line, it's 2/3. And then all we need is a point from that line, which we can use as point B. Point B, it says, is the point -2, 4. So if we're going to write the equation in point slope form first, remember that point slope form is that y minus y1. We wrote it down yesterday. Y minus y1, we didn't write it down yesterday. We wrote it down last week, though. Y minus y1 is equal to m times x minus x1. So right here, we're going to say, y minus, what's the y value of coordinate B? What's the y value of coordinate B? 4. So y minus 4 equals the slope of that line, which is 2/3, times x. If we subtract the x coordinate of B, down for just a second. If we subtract the x coordinate of B, the x coordinate of B is -2. So if you subtract -2, what's an easier way of writing x minus -2? X plus 2, exactly. So we're going to say x plus 2 in parentheses here. And the reason why we're doing this math here is because it wants us to write the equation in slope-intercept form, so we have to distribute the 2/3. So that'll be y minus 4 equals 2/3 x, and then 2/3 times 2, just multiply the numerator by the whole number. 2 times 2 is 4, so that'll be plus 4/3. And then the last thing we need to do to get y by itself is what? Because we're trying to get y by itself. What's the thing we need to do to get y by itself from over here? And we won't actually have to show that work. I just need somebody to tell me, how would we get y by itself? There's just one more thing to do. What's that? Add 4 to both sides, yeah. So we're going to get y equals 2/3 x. And then let's just use our calculators. 4/3 plus 4. So I'm going to open up a fraction. Let's see. Mode. Math print. Okay, opening up a fraction here. We're going to say 4/3 plus 4, because we'd have to add 4 to both sides. 4 would combine with 4/3, not the 2/3 x, because it doesn't have x. So 4/3 plus 4 is 16/3. So plus 16/3. Which, if you're thinking about like fraction, that would be 5 1/3 in terms of if we're using whole numbers or not. So that'd be 5 1/3. Now, if you look at where, and by the way, that will be the y-intercept. And so if you look at the graph here, look at where this line going through the opposite side crosses the y-axis. 1, 2, 3, 4, 5. And there's the 1/3, 5 1/3. So that ends up checking out just fine. So that's the equation of our first altitude. Like I said, these have kind of a few steps to them. So then, now that we have that, we're going to find the equation of an altitude from A to BC. So this time we're going to draw a line from A perpendicular to BC. This one will be easier, I promise. This line will be easier to figure out the equation. So it says the slope of segment BC is what? Who can tell me that? Look at BC. So from B to C, what's our slope? How far up, how far over, and then reduce it if you can. What's that? 2 up, 2 over. Okay. So from B to C, it's up 2 over 2, which is 2 over 2. So 2 over 2, does that reduce? To 1. Yeah, 2 divided by 2 is 1. Anything divided by itself is 1. So the slope of the altitude would be the opposite reciprocal of 1. Or the opposite reciprocal of 2 over 2. What's 1? Yeah, it is. -1. Because if you flip over 2 over 2, it stays the same. It's still 2 over 2. So you'd make it negative, which would be -2 over 2, which is -1. So perpendicular slope is -1, right there. Now it says use the slope in point A. Just like we used the slope in point B for the last line, we're using the slope in point A this time, which again will be a lot easier, because if you have an altitude here and it goes through point A, it has a slope of -1. You can go down 1 and over 1 and put a point there, which basically means if you connect those 2 points and you keep going with it, then it's just going to go exactly diagonally down through all these other points, just like this. Which means we don't actually need to use point slope form on this one. I'll tell you why in just a second. But go ahead and draw that altitude in. This equation is going to be much easier to write than the last one because we don't actually have to use point slope form. We had to use point slope form on the last one because it wasn't clear how to identify what the y-intercept was on the last one. However, on this one, the y-intercept is quite clear. It's this point right there. What's the y-intercept? 4, yeah. It's up 4, isn't it? So 1, 2, 3, 4. So we have a y-intercept of 4. And what's our slope? Slope is -1. So if you have a slope of -1 and a y-intercept of 4, that just means you've got y equals -1x plus 4. So you can just write that directly into slope-intercept form without having to use point slope form. If you know exactly based on the graph what the y-intercept is and you already have the slope, you can just write it in slope-intercept form. If you can't identify the y-intercept by looking at the graph, that's when you need to use point slope and convert to slope-intercept. All right, now, step 3, solve the system equations. This is what we finished up with yesterday. This is where we're going to need to use that upper left margin because we don't have enough room right here to do it. It tells us what the answer is, by the way. We have the answer, but we just have to prove it. So, first of all, if you were to guess where those two lines intersected, because that's what we're figuring out, where the two lines intersect. If you were to guess where these two lines intersect, where the two altitudes intersect, that is specifically, that would be right here. If you were to give me a guess, how far left would you say that is? Like how far to the left is that point of intersection from 0? Like if you're going 0 to the left, is it all the way to -1 or not quite? It's not quite. So what would you guess? About -0.8. Okay, that's a fair guess. And then if you were to go up, how far up does it look like it is? About 4.8. Okay, so if we were guessing, we'd say about -0.8, 4.8. That's a really good guess. Let's see if that ends up being about what the answer is. So we have to solve a system of equations, and the two equations that we are solving for are this one and that one. If you solve a system of equations, because these are both equal to y, we can set those two things equal to each other. So I'm just going to go up here to the left and write those two equations equal to each other. So I'm going to write 2/3 x plus 16/3 is equal to -1x plus 4. Whoop. If you can see that, there we go. 2/3 x plus 16/3 equals -1x plus 4. The right sides of the equations were both equal to y, which means both right sides of the equations have to be equal to each other. So we're just going to set those equal, and then we'll solve for x. This is to solve still, yeah. We're solving for x right now. So we'll set them equal and we'll solve for x. Now, this is just going to be a regular equation, but we've got some fractions involved, which is not going to be a big deal because we've got calculators. So solving this equation, what would be a good first thing to do here? Was that? Like terms, okay. That will involve putting things from one side to another. So what should we do? Add 1x to both sides. I like that. So if you add 1 to 2/3, so 1 plus fraction 2/3. If you want to use just mental math, if you can do this using mental math, feel free. I would highly recommend, though, not writing a mixed number. 1 and 2/3 is correct. 1 plus 2/3 is 1 and 2/3. But improper fractions, they're always a little bit easier to use, in my opinion, when I'm doing math with them, just because we don't have that whole number hanging out on the side. It's all combined into a single fraction. So that's why I usually stick with improper. So that'll be 5/3 x equals, I'm just going to subtract, because we have to subtract 16/3 from both sides as well, don't we? So that'd be 4 minus 16/3 on the right. So 4 minus fraction 16/3, which is -4/3. So 5/3 x equals -4/3. Who remembers what to do to get rid of a fraction? Yeah, flip 5/3 and multiply it by both sides. Good. Multiply both sides by the reciprocal of the fraction by the variable. So we're going to multiply both sides by 3/5. So on the left, those all cancel, and we get x, which is exactly what we want. To get rid of a fraction next to a variable, multiply both sides by the reciprocal of that fraction. So if you flip over 5/3 and you multiply it by 3/5, that all cancels out, which is why we're doing that. And so we do the same thing to the right side as well. Use a calculator or not. What is -4/3 times 3/5? -4/3 times 3/5. Type it into a calculator if you need to. -4/5. All right. So, and somebody else, real quick, somebody type in -4 divided by 5. -0.8. That was a really good guess, Emmy. That's what you said for the x value, -0.8. I would agree with that because that's exactly what it is. And it tells us right down here, look, x value is -4/5, which we just proved using by setting the two equations equal to each other and solving for x. So x is equal to -4/5. Now we have to solve for y. Now there's going to be an easy way and a less easy way to solve for y. The easy way, actually, the way that we would do it is now that we know what x is, and I'm sure you all remember this as well, but the way that we figure out what y is equal to, now that we have x, we could take the value of x, -4/5, and plug it into either this equation or this equation. Which of these two equations looks easier to plug into? The bottom one, yeah. Because -1 times anything is just the opposite of that thing. So let's plug it in to that equation. So we're going to say y is equal to, we can actually just do that right here. Y is equal to -1 times -4/5 plus 4. And if you want to, you can just type that directly into your calculator like that. -1 times -4/5 plus 4. Which is the same thing as 4/5 plus 4. What does that equal? 24/5, which makes sense because it told us the answer down here that the y coordinate is 24/5. And then, Emmy, what's 24 divided by 5? 24 divided by 5, yeah, 24/5. 4.8, which is exactly what you said for the other number as well. You had a couple really nice guesses, -0.8 and 4.8. So you could write these as decimals if you wanted to. You could say, or -0.8, comma 4.8. If the decimals are just like single decimals after the decimal point, you're welcome to write that as a decimal. If it's like a, thirds, don't do it because thirds are 3 repeating with a decimal, so that's not a very good way to write a decimal. But if it's a 0.8 or a 0.5 or a 0.2, go for it. All right, we're going to stop there because this next one is really similar to it and it doesn't give us a graph to work with. So I'm just going to say, let's not do that. It doesn't give us any room to do that. So we're going to call that good for these notes. What I would like to do though, before we get started,